We now start the exercises of this section. In this first one, X is given to be some finite set whose cardinality is n. We then have to prove that its power set is also a finite set and its cardinality is the nth power of 2. And in fact, this is what motivates this notation. We use this notation because of this fact. And a hint is also given, we have to induct on n. So let's see the solution. As a basis for our induction, we are first of all going to consider the empty set in place of X. Since the power set of the empty set is the singleton set consisting of the empty set itself, we have the cardinality of the power set of the empty set then is 1 because there is only one element, but 1 is also the 0th power of 2, and 0 is nothing but the cardinality of the empty set. So that means our claim is true when n is 0, and in that case, of course, the only set is empty set because it's the only set whose cardinality is 0. Now, assume that the claim is true for all sets of cardinality n, where n is some arbitrary but fixed natural number. N is some natural number. We now want to prove the claim for n plus 1. So let us consider a set of cardinality n plus 1. Let Y be a set of cardinality n plus 1. Then n plus 1 is a positive integer, and that is why Y is non-empty, so we can choose one element in Y. All of these things come from some things that we have already proved. For example, you may remember that in the section on finite sets, we have actually come across one lemma which shows that if the cardinality of a set is n plus 1, where n is some natural number, then the set will be non-empty, and then its non-emptiness allows us to choose one element in it. That is also a result. Way back we proved that result, and in fact it was given a name also. It's called the single choice. That is, if you have a non-empty set, then you can choose an element from it. Okay, so now we are going to choose one element. Choose some y in y. Now that same result in the section on finite set, which says that y is non-empty, also says that if we remove this element y from y, then the resulting subset will have cardinality n, 1 less than the cardinality of y. Then this is equal to n. So now we have a set whose cardinality is n. So we can apply our induction hypothesis on this set. Its power set will have cardinality 2 to the power n. So that is our induction hypothesis. By the induction hypothesis, the cardinality of the power set of y minus y is 2 to the power n. But we want to prove that the cardinality of the set y, the entire set y, is 2 to the power n plus 1. So that means what is the power set of y? Its elements are precisely all the subsets of y. Now, depending on this, on a condition involving this element small y, those subsets can be divided into two classes. Let's see how. Let A be any subset of y. If so, the condition that I was saying that involves this small y is whether y belongs to this A or not. It may or may not belong to A. What happens if it does not belong to A? If y does not belong to A, then obviously A is a subset of this and the number of such subsets A is obviously the number of subsets of this, which we already know. This is 2 to the power n. Let's write this also. And the other condition is that y belongs to A. If on the other hand y belongs to A, then what happens? If y belongs to A, then A can be written like this. Where this is a subset of that set again, and because any such A corresponds to one such subset, so the number of subsets A of capital Y that satisfy this condition, that is those subsets of capital Y which contain small y, also are 2 to the power n in number, because ultimately again it amounts to counting how many subsets this y minus y has. Same number, 2 to the power n. the number of such subsets A is again this. Hence, the number of subsets of Y, in other words, the cardinality of the power set of Y is the total number of the subsets of the first kind plus the total number of subsets of the second kind, that is this, which is nothing but 2 to the power n plus 1. So that's just it, because n plus 1 is the cardinality of Y. This completes the induction and proves the claim. This notation is of course motivated by this result, but that is not the only notation for the power set of a set. A more familiar notation is this. Say your set is X, we simply write P of X as the power set of X. It does not matter how you write the power set, you just have to keep in mind that it, by definition, it is the set of all subsets of X. So that's it. And let me just end this brief video here itself, because I am not feeling quite well today. Our next upload is this coming Tuesday, and on Tuesday let's go back to group theory from Herstein. So see you on Tuesday with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.